we seem to be live.
Seems to repeatedly.
Yeah, you can go ahead, Kannan.
Okay. Screen sharing.
Yeah, I think when your iPad sort of locks or something, the screen sharing stops.
Okay, that's not okay. Let's get started. Let's event again, no? Sorry about this. Welcome all of you from whichever parts of India, from all over India and elsewhere abroad. Here it's been a crazy year. Hopefully we can make the best of it by having. But for this year, I wouldn't have done this online course. I would have taught in a seminar room. 2 rooms from mine. So everybody to computational complexity. So before we get started, I just want a few basic things. This is a course, as you know, being taught by Ramprasad Saptarishi and myself. Just wanted to tell a few quick things about the grading policy before we get into the course. So currently, by this one, only TIFR students can credit the course. If non-TIFR students want to credit the course, you can do the grade sideways, but I don't know whether we have any means of awarding you credits. If you want to, I can check with our university and with respect to your university if there's a way of doing it, but right now I don't know this one. So the grading policy, we're going to have 6 problem sets, 1 midterm, 1 final exam, and roughly I think this will be 50% of the grade. This will be 20%. This will be some 20 to 25%. And so in-class presentations and quizzes. We might have some quizzes during. One will involve another 5%, 5 to 10%. 10%. And the 6 problem sets you'll be graded on the best 5 of 6. So problem sets will more or less will start rolling over starting next lecture, Wednesday onwards. Wednesday, the first problem set will be this one. Each problem set will be for 2 weeks. You'll have a respite of 1 week between problem sets, then next. And even those who are not crediting the course, I would suggest you all do the problem sets. Unless we get our hands dirty in complexity, you will not be able to fulfill it. Because the problem sets are going to be a reflection of what's going to be taught in lecture. So it will be good to, even if you're not doing it, attempt the problems and figure out what's going on. So the problems, 6 problem sets, you'll be graded on the best 5 of 6. And problems are due exactly 2 weeks from this one. So I would expect them to be, so if they're due on a particular day, what I actually expect is them to be in with me by 8 a.m. the next morning. So you can spend the night or whatever working on it by 8 a.m. the next morning. So that's the due date. And everybody has a 7-day extra period. That is, you can use the 7-day extra period across problem sets how you want. So if the first problem set, you can use 3 extra days, the second problem set, 1 extra day, the next 7 extra days across the whole term. And that's, so otherwise you will be great. You'll have to turn it in on time. Have to turn it in time. If you take more than your 7 days, that particular problem set doesn't get evaluated. Okay, so that's one thing. Our primary book will be sort of the book by Arora and Barak, Computational Complexity. If you have a copy of the book, it's great, but it's not necessary. We'll be transcribing notes. So I can, if you don't have a copy of the book, let me know. I'll see if I can get an electronic copy or so of the book for you. This one. But in addition to this, we will be using lecture notes across, several lecture notes across this one by, say, Madhusudan, Trevisan. These will be, I'll post them on. So the course has a web page, and you can find the web page link from my homepage, as well as we'll constantly be posting on Academy all the relevant links for this one. So most of the material will So, and certainly at the end of every lecture, I will transcribe. So you need not take notes, because one good thing about this is I will be, the transcript of the lecture, I will post it immediately at the end of the lecture. So you will have the whatever whiteboard I have right now, I'll post it. And of course, the video will also be posted. It's streaming live on YouTube right now, and it will be available on the STCS channel after this one. Okay, so anything else in Administrivia that I had? Okay, that's not there. Let's get to what is this course about. So most of you, I believe, would have done some, possibly done the precursor theory of computation course, where you try to understand what is computable and what is not computable, where notion of Turing machines and recursive Turing machine, recursive introduce this. What we will be trying to understand here is what is easy and hard. Which problems are easy? What computation is easy? Which computation is easy? Which computation is hard? Now, this is a very subjective question. Something is easy for me. Something might be easy for you. It might be hard for me. So, what is it? What does it mean to be easy or hard? This is a very subjective question. How does one even build a theory on this? So, easy or hard, as we said, it's from the eyes of the beholder. So, it's easy to me, it's this one. So similarly, it will be respect to, you'll have to talk about easy or hard with respect to some of the thing. It's hard with respect to the amount of time this particular problem takes. It's easy with respect to the amount of space it takes. It hardly takes any space. So it's going to be in terms of the response. Easy or hard will always, you'll see it will be in, firstly, this is a very subjective question. So we'll try to answer what does it mean to be an easy problem or a hard problem. These are some things which we will try to formalize. These are very sort of meta statements, but hopefully complexity will help us in trying to formalize this notion. And actually, we will see that it's not just easy, hard, there will be other things like randomness. What does it mean to be random? What does it mean to have knowledge? These are various things across the course. We might try to formalize these very abstract meta notions and try to give it a computational, look at these things from a computational viewpoint and capture it. And of course, once we said this, already said easy, hard depends on the eyes of the beholder. What does it mean, beholder? It depends on which type of, with respect to what resource is it hard. So we'll study various type of resources, computational resources, different types of resources. So the usual almost the most standard thing is respect to time. Is it easy with respect to time? Is there a fast algorithm for this? Is there every algorithm takes too much time on it? For example, you would have heard that factoring is a hard problem. What do people mean by that? What they mean is most computers today will take an enormously long time to solve factoring. So it's better. Time is the computational resource over there. You can talk of other resources, space. So if the few of you who possibly were in the toolkit course earlier, so space was the resource being talked about there. You had a stream and you wanted, so space is a resource. Sometimes we might talk about, we might later on come to random, we might come to randomized algorithms. We must ask how much random coins one needs to toss in the algorithm. So that is a resource, we'll consider that resource. And then they will come to other algorithms in which it's not solved by a single player, there are multiple players. For example, you have solving a problem on the net, or right now we are talking. So the important resource over there is the bandwidth. So then you will talk about the communication or the interaction between them. So some problem might be easy with respect to one resource and hard with respect to another resource. So we'll consider a plethora of resources of this type. And then sometimes we'll also try to see if we can do an interplay between the resources, across the resources. And given that, we will also look at But how do we come to all of this? We'll basically, our motivations will be we'll look at some standard problems. We'll look at some what I think are interesting problems. Ram Prasad thinks are interesting problems. We'll look at things which have been this one, compare and contrast several of these interesting problems that occur very naturally. And compare them somehow against each other. Sometimes it might say, how can you compare these two problems? They were apples and oranges. How do you compare this problem against this? We'll try to build up a theory at how to compare problems. In fact, this is the notion of reduction, which you already possibly saw in theory of computation. We'll import that notion and give it a more complexity theory framework. And possibly this is the biggest export of computational complexity, the notion of reductions. And this is something which we will see over and over again. And even in the very end of this lecture, we'll spend a fair amount of time on what reductions are. In fact, the next three, this lecture followed by the next two, will do reductions. So this is what I mean by compare over here. We do compare, we take two problems, want to understand what does it mean. Is this problem easier? Is this problem harder? To compare, we'll build the notion of a reduction. All of this is because we have some interesting problems. And who says problems are interesting? So and we build sort of phenomenon or classes around these interesting problems. And that is going to be, so the whole course will be based on certain problems. There'll be certain problems will be sort of like our guiding posts. We'll take a bunch of problems. I'll start off with listing a dozen problems that we would have seen at various places and say that these problems and trying to understand how well we can solve them is basically trying to understand the algorithms that we can solve them. I'm trying to understand why we can't solve them. These problems will sort of fall the lamppost for us and to find out understand these various notions of easiness and hardness. Any questions? By the way, feel free to, it might be an online course, but feel free to stop, ask me. Either you can just interrupt me during the lecture or you can put up a chat or anything, but feel free to just interrupt me during the lecture. Okay. So let's start off with, I'm going to list a bunch of problems which I think are interesting in my viewpoint. And then we'll classify them as possibly what interesting or hard. So let's start with some very easy problems. So your one problem is parity. So what's parity? I'm given an n-bit string. Compute the parity of the strings. So that's one problem we can talk about. So is this an easy problem, a hard problem? This is something we should have done. It's easy. We believe it's an extremely easy problem. You just look at the bits, you can just scan it left to right and compute the parity. You just have to have, as long as you have an XOR gate or this one, you can do it. Let's go to something a little more. This one, say.
This means going mod 2, right? Or just adding.
Yeah. Pardon?
This means like going mod to the sum?
I'm just going mod 2. So it's just the usual parity that one, it's the XOR function. It's mod 2. Yeah. I'm summing the n bits mod 2.
Yeah.
Yeah. So let's take something else. That's something which we've sort of learned in high school, integer multiplication. That's certainly a little more harder, but on the other hand, it's a very basic problem. We have seen it starting from high school. So here, what's the problem here? You're given two numbers A and B in binary notation. Of n bits each. You can think of n digits the way we did it in high school, in elementary school or middle school. Compute the product A dot B. There's also an algorithm we're extremely familiar with. All of us are taught this. And in fact, what's the standard long multiplication? How much time does this take?
N square. And the number of bits.
N square. So if it's n bits each, that's n square bits. But actually, there are much faster if you use Fourier trans. If you use this one, you can get much faster algorithms, which today I think run in n log n log n, or even faster. I think we believe once. Yeah, integer multiplication. We can ask connectivity. I'm just going to give a sort of a list of problems, and actually, if you see, the course will be these problems will actually be the sort of the problems we will be discussing. We'll be building interesting phenomenon for these classes. Connectivity is you're given a graph G. So let's say some vertices and edges, and two specific vertices, an S, a source, and a target. And question is there a path? From S to T. And we designed algorithms for this too in sort of an algorithms course. Run depth first search, breadth first search does this. You could ask questions on this. You could ask, is this what happens if you can ask, is the graph directed, undirected? And we know algorithms in both cases. We know algorithms even the directed case, which is more general. And we will see that how actually these problems become different based when the problems are directed, undirected. Next problem I'll talk is a more possibly it might have been one of the highlights of an algorithms course you're given. Given a graph, say given a bipartite graph, G is LR, the left-right edges. Does there exist a perfect matching? But ask this problem, and if so, find one. Okay, that's another of the problems. Okay, so now, so far all these problems are problems for which we have seen algorithms, and we know how to solve them. You would have seen algorithms for these problems. I'm going to enter slowly into problems possibly for which we do not yet have efficient algorithms. So one example which you possibly have seen, if you have any, this one is what's called the satisfiability problem. Is given a Boolean formula. We'll actually, just listing a bunch of problems, we'll actually go back into each one of them and see what it means to be easy or hard for each other. It seems that I've already listed a bunch of easy problems, I'm going to a bunch of hard, but I'll list them out and then we'll see. Given a Boolean formula phi, is it satisfiable? I'm going to make this problem a little more complicated. I'm going to talk about what I'm going to call number set. Number set is a similar thing. Given a Boolean formula, phi, find the number of satisfying assignments. Previously, I just wanted to ask, is there a satisfying assignment or not? I'm asking statements. So at least with the very statement, this problem is at least as hard as SAT. Because if I can solve this problem, I can certainly solve SAT. SAT is just asking is the number non-zero or not. This you're asking the exact number. What we'll try to understand is it any more harder than SAT? Is it just as hard as SAT? What's the relative complexity between these two? Which is certainly number SAT is in some sense at least as hard as SAT. And we'll formalize what this at least as hard means. Furthermore, is it just as hard as SAT, or is it harder than SAT? And these are things which we will see in the course. The next problem which I'll talk about is what I'll call the permanent. So what's the permanent? The permanent is it's like you're given a matrix, given a square matrix, say matrix M, and let's say it has just 0, 1 entries, n cross n. You're given a matrix M, M11, M12, M1n, M21, so on to Mnn. And what I want to compute is the permanent of this matrix. What do I mean by the permanent? It's almost like the determinant. Most of you are familiar with the determinant. The determinant goes over all permutations of Mi, sigma I going from 1 to n. The determinant usually has, so if I had put sine sigma, that's the determinant, but I'm not going to put sine sigma over here. So the permanent is the sort of the in some sense it is, sort of the unsigned determinant. This seems on the face of it very much like the determinant. Determinant, possibly you have seen any course in linear algebra or engineering, you would have seen determinant is not too hard to compute. You can use standard techniques like Gaussian elimination and compute the determinant of a matrix. The permanent, on the other hand, as we'll see in several lectures from now, is actually a very different beast. The permanent is going to be, we don't yet have any efficient algorithm for permanent. And this is something we'll try to understand why we don't have efficient algorithms for permanent. So that's one problem. Another problem which we'll talk about is what I'm going to call CNF minimization. What is this? So once again, you're given a Boolean formula in CNF notation, phi in CNF form, in conjunctive normal form, and a number m. The question is, does there exist an equivalent? I have to define what that means. CNF psi, such that psi is equivalent to phi, that's 1, and the size of psi is less than or equal to m. What do I mean by equivalent? So two Boolean formula phi and c are equivalent if for all inputs a, phi of a is equal to c of a. That is, they as functions, they compute the same function. So what I'm asking is, I'm giving you a Boolean formula phi, and I'm asking you, is there a CNF which is even small, which is of size smaller than phi? Can you do this? Okay. So let's have a bunch more problems, but I think it is taking much longer on the notepad than on this one. So let's just go over them one by one. So we already saw parity. So which of them are easy? So 1, 2, 3, and 4 are something we already saw they have algorithms. 5, 6, 7, 5, 6, 5 you possibly have heard is hard. If 5 is hard, 6 has to be hard. We believe that. 7, we will show that it is hard. What about 8? What are your thoughts on 8?
Can you scroll down to 8?
Something's gone. Yeah. What about 8? So I give you a CNF and a number m, and I'm asking you, is there a CNF of even smaller size than this particular CNF?
It seems hard.
It seems hard, but can you give me a...
So in order to check that if they're equal, we need to go over all the valuations, or so I think it should be as hard as number set.
Like
No. So
if
this is what you're suggesting is one way of doing it seems to take the same amount of time as number set. But this is still not a proof stating that this is as hard as number set. What we need to show is any way of doing it will take the same amount of time as number set. One way of solving this is similar to the way of solving number set. You go over every possible assignment and solve.
like if we take m equal to 0,
Yeah.
then I mean so if we take m equal to 0, so that means the psi can only be true or false. Then so can we reduce this to set? I mean, so any as in...
Yeah, can you? Okay. This is actually might be a part of your first problem set.
Okay,
So
can we?
Yeah.
So can we like take the AND of both of them and take a OR of not of both of them?
So you have only one formula. You only have phi with you. Psi is not given to you. I'm asking you, is there a psi which is even smaller than m that computes phi?
Okay.
But you can take OR of both of them. I don't have, I have only phi in my hand. As an input, I have only phi, and I'm asking you, can I do something smaller?
Okay, yes.
Okay.
So we can generate the possible sets of size, and then look at the
So how many size are there? So
yeah.
So the number. So that is an algorithm. Is it an efficient algorithm? So let's assume something has size m. What does it size m? That means the description of it is of length m. Now,
So
how
that
many
will be
things?
2 to the power m, right? That
will be 2 to the power m. Therefore, you just going over all possible size itself is 2 to the power m possible size are there. You have to go over all of them. And then furthermore, now you need to check if that psi is equivalent to phi. That seems to be another running over all the 2 to the power n now. So it seems to suggest as if it's a 2 power m plus 2 power n. So this is an algorithm, certainly. You can go over all size and then go over all possible assignments and check if this psi matches this and check if there's one of them. But it's not efficient in our, what I would like to call efficient. Right now, it is an algorithm. It's not something we could typically run in practice because these run in exponential time. Why is exponential time bad? We'll come to later. Yeah, who was
like we can, so we are given a phi, so we take negation of phi and then we give it to this problem. This, suppose this has a oracle, then we will give to this oracle. Suppose it gives true, then that means phi is satisfiable. I mean, suppose it gives false, yeah, then that means phi is satisfiable, right?
why?
Because if negation of phi is false, then phi is always true.
No, but what do you mean false? What? So what is the so
Yeah, so I am saying, so suppose this 8th problem has this oracle.
Yeah, so suppose there is an, I give you a magical subroutine that I claim solves it. But if you give me phi and m, and this magic box will miraculously tell you if there exists a C such that psi is equivalent to phi and psi computes, and psi is this one. Yeah.
Yeah, so if you give, so you take a
Let me give you one more thing. Let's suppose assume that the magic box outputs the psi to you. Right now, it's the magic box. The way they stated is only asks you whether it tells you whether a psi exists or not. Suppose it gives you psi. How would you do it?
So you take phi, you take negation of phi, and you take 0, and you give it to this magic box.
Okay.
And then, if phi was satisfiable, then negation of phi would be contradiction. I mean, oh, okay. Okay, sorry. No, it won't work. I mean, both of them could be satisfiable. Phi and negation of phi.
They could be satisfiable, but slight this one to your problem. So it should have stated it this way. So we talked about SAT.
Yeah.
So a related problem to SAT, my version of it, let me just say, this is not how I wanted to do, but given that you mentioned it, let me say, so you can talk about some type of SAT problems are what are called DNF. You know what DNF and CNF, I'm assuming most of you know what DNF. So I give you a DNF and I can ask you if a DNF, is it satisfiable? If I give you a DNF, is it satisfiable? Is that easy to check?
No, right.
No, DNF is easy to check. You just have to take one term, and if you set it to be true, the DNF is it's easy to satisfy a DNF. It's what is hard is to unsatisfy a DNF. For a CNF, it's the other way around. For a CNF, it's easy to falsify a CNF, but it is hard to satisfy it. And we will see the one-sidedness of this. So I give you a DNF. And you could now do the problem. So I give you a DNF and I ask you if it's satisfiable or not. Sorry, ask you if it's satisfiable. That's an easy question. Ask you, is it not satisfiable? Actually, this happens to be, we don't know how to solve it. And if you stare at it fair enough, this happens to be equivalent to the SAT problem that we mentioned over here. And I claim what you said now exactly will work with this. I give you the negation of this DNF, that's a CNF formula as input to it, and ask, is there a shorter thing that computes it? If the shorter thing happens to be of size 0, then it has to be a tautology, which is the false statement, which is a true statement, because it can never be false. A DNF is always satisfiable, and that will tell you this one. So what I'm claiming, what we have discussed just now is basically that of the following nature. We didn't formalize all of this. In some sense, say that if there exists an algorithm for CNF minimization, then can solve SAT. We didn't formally go into it, but it's sort of, this is a flavor of what you were trying to say, and I made it a little more formal, but we will see if we can done. But this is what. So what does it say? In some sense, it says problem 8 is at least as hard as, what was the other problem? Problem 5.
So if this m is like n times 2 to the n, then it would be easy to come up with this psi, right?
Pardon?
If this m is like 2 to the n or something, then it would be easy to come up with this psi, right?
If m is 2 to the n, yeah, if m is large enough, but the part is m is also part of your input. So m is part of the input. So what we'll actually see, what we'll see over the course, actually we'll relate several of these problems over the course. So one thing, certainly something which you've already seen, you've seen the Cook-Levin theorem, that SAT is in some sense a hard problem. It captures several, we see that SAT is NP complete. We'll see this. But we'll do more other things. We'll see interesting thing is number sat and permanent are sort of equivalently hard. We'll define what this means. This is a big theorem of Valiant, and we'll prove this. That is, if you give me an algorithm to solve one, I can solve the other. If you give me an algorithm to solve one, we'll show that these both problems sort of live together. So permanent, despite its simple description it looks like a determinant and stuff, it's much harder. It seems to be as hard as number set. Not as hard, and we actually prove it formally. We'll show it's not just as hard, it's exactly as hard as number set. If you can solve permanent, you can solve number set. If you can solve number set, we can solve permanent. We'll go this. Then we'll show something even more stranger. We'll show that somehow SAT, CNF minimization, which we already saw just now, is as hard. This arrow just basically means the problem on the right is harder than the problem on the left. We'll show that CNF minimization is somehow harder than SAT. And in some sense, we'll also show number SAT is even more harder. So in some sense, this will be results of Stockmeyer and Toda, which we will. So this is what we will sort of do. We'll take problems, we'll look at problems, some interesting problems, we'll see why they are interesting, and we'll build phenomenon about them. Ideally, I would like to show some problems take a lot of time, are hard. Unfortunately, we are far from doing that. We have not, as a field, it's still a fairly young field. I don't know how to through hardness, but what we'll talk about, we will relate problems. So what we would like to show, what we would like in this course, is statements of the kind, problem A is hard, or problem B is hard. This is what we would like to show. In contrast to an algorithms course, you design efficient algorithms. You want to say this is an efficient algorithm. I would like to say in this. Unfortunately, we are far from doing this. Fortunately, we will be able to do a few things, but unfortunately, we are far from doing this. What we instead have, over the course, we'll come up with several conjectures. We'll assume that A is hard, B is hard. We'll assume several problems. What we will be able to show is we'll be able to relate the hardness of one problem to the hardness of another problem. This is something we are pretty good at doing. And this is what most of the course will actually be doing. We'll be doing the notion of this problem is as hard as this problem. This problem is as easy as this. We unfortunately do not know how to show a particular problem is hard. I would be delighted if we can show factoring is hard, or SAT is hard, or number SAT is hard. We won't be able to show that. We don't yet have the technology to show this. What we'll instead show is we'll consider these problems. So we'll do the next best things. We'll consider how hard is this problem. Is it harder than the other problem which I care about? Is it easier than this other problem which I care about? So we'll sort of build this phenomenon around classes. We'll take a particular problem, fine. We don't know how to solve it. We'll compare it to another problem which we either know how to solve or don't know how to solve, and compare these two, and we'll build this sort of structure. So what we'll sort of do is, for instance, suppose we'll show that this is the notion of reduction, which second.
So this just means that hardness is sort of relative to something else, right?
In the sense?
It's you can say that a problem is hard if it sort of relates to some other problem, right? Like,
so what does this one hardness mean? So let's actually. So how do?
So Prahlad, the screen appears to be frozen. Yeah.
I don't know why. I think I just logged out completely. 1 second. Okay. So this will come to our main central notion of reduction. By the way, this class is going to be sort of a hand-wavy class. From next lecture, I'll be a little more formal about things. The notion of a reduction. So this is what I'm going to talk about. I want to say one problem is hard as another problem. What does this mean? So you have two problems, say A and B. So A could be SAT, B could be CNF minimization, A could be SAT, this could be number SAT, this could be sharp SAT, this could be permanent. And I want to capture the fact that A is no harder than B. I want to capture this somehow, this fact. So one way of doing it, typically if you look at an algorithm, so suppose I give you a subroutine, I give you a program that solves B. Then can you use that program to solve A? If you can use that, then that means A is no harder than B, because you can use the program. This is what I'll call subroutine reductions. Can use a subroutine for B to solve A. That's one kind of reduction. And if you're done the theory of computation, you might have seen this is called what are called also called Turing reductions. Some of you might have also heard of the other notion. I will not define it, but many-to-one reduction. This is a more special case of subroutine reductions. In what sense is a special case? We'll come to it shortly. You might have heard of this, either they call it Turing reductions or CARP reductions. Sorry, many-to-one reductions or CARP reductions. It's a very specialized kind of reduction, kind of subroutine reduction. And you might ask, why do you want to do this? It's going to be a smaller class. It's going to be easier to search for such reductions. So we will do such sort of. So we will build this out. So what will happen when you do this? So you have several problems: A1, A2, A3, A4. These are problems. You'll be able to show one is smaller than the other. The other is we'll build reductions of this kind. So we'll build this sort of this, and among them possibly you build another set of classes B1, B2, B3. Then another class. You show that all problems here reduce to this. So you have a bunch of classes A here, a bunch of problems B here. And it so happens among B, these are all equivalently hard. That is, you have reductions running either way. For example, one example over here is A3 could be SAT and B could be number SAT. This could be permanent. So we have all of these problems reduced to these problems, and these problems are equivalently hard. So in some sense, the problems in B, the problems in B are sort of equivalently hard and capture the hardness or easiness of all problems in A union B. So in some sense, we'll call the problems B as sort of the complete problems. So we'll define a class called A union B, and we'll define B to be the complete problem for the class A union B. So we'll come to this. We'll sort of do this sort of thing. We'll want to study a problem. We won't be able to study a problem. We'll study related problems. We'll build this sort of web of reductions, and that will lead us to what we'll eventually call complexity classes and so. Okay. So that is the high level is what is going to happen in this course. We'll be taking interesting problems. Most likely we'll be starting off with these 8 problems. These 8 problems, by the time we study them, it will be actually 20 lectures in the course. We'll study these 8 problems. We will look at interesting phenomena around these classes. Each of these problems are going to lay basis for a lot of other classes. For example, let's even go to, we talked everything with respect to easy and hardness with respect to time. One problem with respect to connectivity, for example, connectivity, we know it's an easy problem with respect to time. We run DFS algorithms, BFS algorithms. Now, suddenly, if you change the resource, say you change the resource from time to space, does your notion of easiness and hardness still remain the same? Things might change completely. So what we will see later on is actually, if you change the resource to become space, actually connectivity, the fact whether the graph is directed or undirected is going to make a big difference. We will see that it's actually easy with respect to undirected graphs. With directed graphs, we do not know, and we presume it's a hard problem. And yeah, so this is what we'll do. We'll be sort of motivated by these problems. We'll build. We can't study a problem, so we study related problems. We'll build this sort of reductions between problems that will lend itself to what we'll call these complexity classes. For example, the class around SAT, which we'll build eventually, will be NP. The class around the number SAT, which we build, will be called sharp SAT. The class around directed connectivity will be NL. These will be classes which we will describe, and we'll see them. It will become as a natural consequence of what we're doing. But so this is sort of a high level, very high level of what we're going to be doing in the course. But we need to get our hands dirty, so we'll have to first figure out, start off with which model of computation are we going to work with? Does it matter at all? These should be model independent, but we need to stick to some model. So we will go to, so you could be working on a RAM, you could be working on a Turing machine, you could be different things. Is the notion of hardness or easiness, does it depend on the model? Ideally, I would like the notion of hardness and easiness to be model independent, to be an abstract enough notion. Model independent. So I don't know how to define it and make it model independent. What we instead do is we'll work with a model which sort of captures most other models of computation. So we'll work with a model which most of you are already familiar with. We'll work with a Turing machine model which captures all reasonable models of computation. It seems to capture all reasonable models, and it seems to efficiently. There are exceptions to these, in the sense that does the Turing machine model, which I'm going to talk about, capture the quantum computer, which people are a lot talking about. Even a few weeks ago, if you've been following the news, there was a quantum attack on the MD5 hash function. So there's a different notion of computation. We will, if time permits, I'll go to the quantum notion, but the notion of Turing machine, which we are familiar with, is not known to efficiently capture all models of computation. For example, we do not know whether it captures quantum model of computation, but most reasonable models of computation, it is, at least we believe it does capture, and we will, as an initial start, we'll work with trying to understand this in notion of what is a classical Turing machine. We'll go on to other models of computation later on in the course. So most of you, we've done theory of computation, you know what a Turing machine is. So I have about another half an hour to go. So this half an hour, we'll just get our hands a bit dirty so that we come up with the same language when we talk with respect to Turing machines. This is how, if you're writing a problem or a problem set, this is how I would like you to do it. This is just to get a language free. And then hopefully once we have this, we will not talk about Turing machines ever again in the rest of the course. This is just to set. So what is a Turing machine? By the way, any questions so far? I'm going to get a little technical for the next 20 minutes or so. Any questions? Okay. So what's a Turing machine? So let's work with what's a Turing machine? Can anyone just quickly tell me what a Turing machine is? How would you describe a Turing machine? And then I will formally define. Possibly some of you have seen it already. Most of you have seen it, yeah.
You have a tape on which you can write down a few symbols and maybe work on it.
Yeah. So okay. So the Turing machine is going to have several components to it. One is a tape. So in fact, I'm going to give it several tapes. I'm going to give it, say, multiple tapes. One which I'll call the input tape, and some others which are work tapes, and possibly the last one to be an output tape. So the first parameter I'm going to say, K, is going to be the number of tapes the Turing machine has. Okay. Then you also set symbols. So there are symbols that are written on the tape. So the next thing is what's the alphabet of the tape? What can be written on the tape? That's the alphabet we're working with. And this can be, certainly we want to include, the alphabet should have at least 2 different symbols. So let's put 0 and 1 for it. It could have more symbols, so at least 0 and 1. And then I want certain specific other symbols. I want what's called the start symbol and a blank symbol. So I want the alphabet. These are the symbols that are on this one. What else did we say? What else? Okay, go ahead. Whoever was saying I interrupted. Yeah.
The states, a final state and a reject state.
Yeah. So how does So before that, how does this operate? This is operating by, there is sort of a
transition.
there's sort of the head of the tape. There's a head which is residing, which is reading some element of each tape. So it's there, and it keeps moving left, right, and this one as it reads. So the head, there's something called the states of the state space. So there is a, so the next is specified gamma, then Q, which is the state space. State space, and this certainly includes, as Satyajit said, 2 specific states. One is the start state, how you're going to start off the machine, and possibly a state which says once you come to this, you stop the machine, a fault state. It possibly includes several other things, but these are at least 2 specific things it should include. And then
you have a transition.
Yeah, and then mainly the most important thing, which is the transition function, the rules of the Turing machine. So what is the transition function? So what's the transition? It says how the head should operate. So the head is in some state, so its input is a Q, and it gets to read the alphabet on all the K tapes. So it's gamma to the K. It gets to see the K alphabets. It's in some state Q. It gets to see the Q, this ones, and based on that, it's going to make the next move. So what do you think will be? So it's going to go to a different state, and then what else?
Prahlad, I think the screen froze again. I don't know why that's happening.
Screen froze again. Okay.
Actually, I don't know if it's happening to everybody or maybe it's an issue on my side.
No. I think because I can't.
Okay.
We can see that only rules of Turing machine is written right. Maybe Prahlad is writing something.
No, it's possibly my. I should figure the better way for this. I think my iPad Zoom has, just give me a second. Anyway, I think my Zoom is reconnecting on the sort of. Anyway, that's. So what were the rules actually? Can somebody go ahead and what were the rules?
So the screen share has stopped.
No, I know it has stopped. I have.
Okay.
Yeah.
So you have a head, then the contents on the tape, and you either move left, right, change the contents of the tape, and change the contents of the head.
Okay. Yeah. So it's good. So it first tells you how to change the state, and then tells you. Can you see my screen now?
Yep. Yeah, we can see it.
Yeah, it's going to tell you how to change the contents of the tape. So it's gamma to the k. It's going to tell you what's the new. It sees a bunch of k states, k symbols in a particular state. I'm actually going to make it gamma k minus 1 in the sense that the input tape it's not allowed to. The input tape it only gets to read. It cannot. So this input tape is what I will call read only. Sometimes we'll make it write also, but let's for now work with just the input is read only. So it only gets to write on the other tapes. And then it has to also make a transition. So you have to tell me whether it goes left, right, or stationary on each of the k tapes. So that it goes left, right, or stays in place. And this is how it progresses. So these completely specify. So it's this 4 tuples. So Turing machine M.
So can it read from the output tape?
Right now, I'm going to let it read from the output tape. We might later on talk of things in which the output tape is write only and you don't get to read it. Right now, I'm going to treat the output tape as this one. So it's specified by this K, gamma, Q, and delta. Okay. And we will always work for now for this course. Actually, let me before I come to that.
Pralad?
Yeah.
Does it matter whether the output tape is read only, like write only, or both read write?
So right now, I'm going to allow the output tape to be read write. So the only restriction I put is the input tape is read only. All the other tapes are read write tapes. Later on in the course, at this point of time, it really doesn't matter. This one, there will be a point of time, and when we consider one of the other resources, a specific space where we will have to restrict what the Turing machine does on the output tape. We can't make it a read tape on the output tape, and also we can't allow it to go backwards. We have to let it go only one direction. So when I come to that resource, we'll talk about it. But right now, all tapes. So the input tape, the input is read only. And you can go left, right, both, and stay on. And the work and output tapes are read write. And you can go left, right, stay. Let's follow this convention. Now you can ask, if you follow this other convention, can I still do it? You can. We should ask, are these different models of computation? Can we compare them? We should be then check these questions. We'll try to do this. For that, I wanted to get to one thing to even compare them. I need one more definition before I can get to. So now we're going to just ask, what does it mean when I have a machine like this M, say, computes a function f, say a Boolean function or even a non-Boolean function of this type. What does it mean to say that a machine computes? So what does this is a technical term? What do we mean by this? I'm just being very pedantic here. So what does it mean? What does it mean that you Turing machine? Now that I have defined a Turing machine this way, what does it mean for the Turing machine to compute f?
Maybe it outputs from the output tape f of x.
So what I'm going to, yeah, exactly. So what I'm going to say is, that is, if, I'll say this is the case, if the machine M is initialized with this on the input tape. The input tape has X input tape and blanks on the other tape. And with Q start as the start state. Then you let the machine run. You just keep the rules of machine keep going. Each step it takes one step, or it runs the rules transition function. It applies the transition function repeatedly. Function delta repeatedly. So it might end, it might not. So say at some point of time, when I say it computes, it says it eventually does go into halt state, into QH, the halt state. And at that point has fx written on the output tape. This is what the statement m computes f function means. It's just this loaded statement. It says there is this machine which you initialize. If you initialize this way, you write x on the input tape, blanks on every other tape, start it off QS, and let the machine roll. Make it apply its transition function one after another. Eventually, it will go into halt state. It has to go to a halt state. That is, if the machine is initialized this for all inputs. So this should be the case for, that is, for all x in 0, 1 star, it should do this. It's not that it does it for a few of them. It should do it for every single, this one, it should do it, and it should go finally halt, and it output f of x.
Excuse me.
Yeah.
So in the other tapes, so can the initial state of the other tapes can be anything? Or
No. It's blanks on all the other tapes.
Okay.
That's how you start. When you start a configuration, the only configuration is the input on the first and blanks on the. You start with white paper at every single time. When you start the problem, when you go into halt, whatever you have on the final, this one, you throw away all the work tape. I don't care what's written on the work tape during the thing, but what's written on the output tape is the final, should be f of x.
Also, one more technical doubt: like, should all the work tapes also start with the start symbol?
That's up to our convention whether you put it to. So you can say start. So because I'm having one-sided tapes, you can assume that there's a start symbol over here just to indicate to it that this is the extreme left end of the tape. There's nothing on the tape beyond it.
Okay.
So let's assume that all the tapes actually start with the start with.
It again froze.
Is it because
I don't know if your iPad is connected to a weakish network. Yeah, is that why?
that could be the reason? But I think I'm connected. Yeah, hopefully next time onwards I'll figure out a way to make this better. Yeah, but even now, so I have my notability on, but it does not have.
So, or maybe do you want to try it out with the AirPlay thing?
Let's see. So then let me just log out of this 1 second. Do you see the screen now?
Yeah. Now it seems fine.
Yeah. Possibly the size of the screen is smaller in this than that. Doesn't show the whole screen. That's fine. So this is what it means when you say m computes f. It means that every single input, if you initialize all the tapes this way, you started off with q start, it goes, and this is what we mean by the statement. Sometimes we would not only say this, we will state all of this is being very. We further want to say m computes f, this particular function, say in some time t, So t is some function, takes n to n. It takes, well, what does this mean? It takes on input of length n. I want to say the machine takes tn steps. So sometimes we would add this extra, this one, we'd add this in time t, where t is some function of this form. What does that mean, takes tn steps? It means it's going to be applying, that is, the transition function delta is applied t mod x is applied at most t mod x time on every input, on each input. That is, if you start off with x, not only does it halt, but it halts within t mod x. This is when I mean, this is the statement. Now, sometimes I not only say to m computes a function, I'll further say m computes a function in a particular time t. So this is sometimes the various notions for this. Just only 1 second. Yeah, so no, I don't want to say anything over here. So now the one question that can come over here, one thing to be careful about is, what are the t's that are allowed? What are the time t functions that are allowed? So it seems like a technicality. So certainly the t which we are thinking of, t of n, I want to think of functions. The examples of this are sort of like t of n is, say, n, it takes n square steps. It takes 2 to the n steps. It takes n log n steps. These are the tn functions that I think of running. These are the tn's which one is thinking of doing. But I can be sometimes perverse and say tn is the number of steps taken by the nth Turing machine on, say, the nth on input on some specific, on say on some other on the nth input. So I have some ordering of the Turing machines and some this one. This is also a well-defined function, but this sort of a perverse thing I'm putting. So I don't know how to compute this tn. This tn doesn't seem like a very natural tn. This sort of a tn seems a very perverse tn to work with. And certainly I don't want to work with these sort of tns. The tns I want to work with are more like these guys. But how do I eliminate these? So yeah.
Tell me one more example where sort of a function which is not something that you use for tn.
You want another? So what's another example?
So the ones on the left seem the most obvious ones, or the ones that you mostly come across.
Yeah.
On the right, the tn defined on the right doesn't seem like a very natural definition of time that you.
Yeah, but how do I rule this out? How do I rule this out? So I want a definition. I want to allow, say, so we're going to define what we're going to call. I'm going to define, this is exactly what we're going to try to do. I'm going to toss out some t's. So I'm going to say t is t time constructible. I'm going to talk about a notion of time constructibility and say that I only allow certain types of t. We don't want to be too restrictive. I don't want to say I want to use only polynomial functions, exponential functions. I want to be fairly specific. I want to say I can use any function, but I certainly don't want to do. Why is this? Why is the function in orange here a perverse function?
Maybe because the number, you're dependent on a number of Turing machines, right? Like,
no. So suppose I know. So the number of Turing machines is just take the Turing machines. You can write them in some order. I pick the nth Turing machine and just run it. So why can't I do this? I pick the nth Turing machine, run it on the nth input, find the number of steps, and that's the answer.
So just kind of a guess, is it? So computing TN would take more than TN time?
So that's one thing. Question is, TN should never take, I don't want to use a function TN, where computing TN takes more time than TN. So that's one very good thing. So I want time constructible functions, the functions I want to talk about. So I don't want to throw the hardness of TN into the definition of TN. TN should be such a function such that you can compute TN certainly in time TN. That's one thing. But when you're saying that, you must be able to compute TN. That is, there must be a machine that is able to find out what TN is. The definition that I gave over here, is not even clear it computes, because it does not halt on every input. There are certain Turing machines, we already seen in uncomputability, it doesn't halt. So it doesn't satisfy. So firstly, as Varun said, we want a Turing machine that computes TN. And that's the first thing. We want it to, on every input, it should be able to compute TN. And furthermore, not just compute it, it should be able to compute it within time TN. These are the two things we want. So we will talk about, so when I try to say time TN, so this is what? So T, function n to n, is T time constructible. I'll just call it constructible, time constructible. If a couple of things happen. One, firstly, Tn should be greater than or equal to n. I'm going to always look at the input fully. The input is n bits long. That's one. Two, what I want is exactly what Varun was mentioning, that there exists a Turing machine M that computes T. And what do I mean by that? That is, that computes T, that computes the, let's say computes the function x going to T mod of x written in binary. So give me any x, it should be able to output T mod of x within T mod of x time steps. So, and you will see why we do this sort of definition. It's to get rid of some perverse examples of T. Once we have this, so we will work, when we say some time T, we will work only with time constructible T's. We will not talk about these sort of orange examples, which are, these are perverse. You're putting all the hardness into definition of T. I don't want T to be a hard function per se, this time constructible thing. It should be something which, firstly, it allows you to read the whole input. That's the first condition. The second condition is, you must at the very least be able to write down what T is in time T. And that's what the second one is stated. So we assume these, and certainly all the things on the right, on the left here satisfy this property. This doesn't satisfy this property because it's not, firstly, it's not even computable. Forget about the number of steps it takes. It's not even computable. Sometimes these machines don't halt, so I won't be able to do it. Here, but I'm asking, not only can I compute it, I must be able to compute it within so many steps. So we'll work with such sort of response. Okay, why did I give these examples? I have 7 more minutes. I want to say, why did I say this? I want to say we work with a very specific definition of, Turing machine. But I want to say it's actually amazingly robust. You can vary the definition in various ways, and you really don't change the notion of what it means for a machine to compute a function. You tweak it around this way. You can say, I work with this. So one thing should be very clear, that is, you could work with any alphabet, as long as the alphabet, any finite alphabet, What do I mean by this? You give me a machine that takes some alphabet gamma. I can give you another machine with just with a binary alphabet that simulates the original machine within too much time. So actually the claim I'm going to make, we'll see this proof next time, but I want to say is, suppose M computes F in time T with alphabet gamma, then there exists a machine M prime that computes F in time, not significantly more, it just possibly some big constant log gamma times T with alphabet, with a Boolean alphabet. So the alphabet really doesn't matter. Which alphabet you work with, I want to say that's one of the claims we will see. Actually, can one of you quickly tell me, if you quickly see why this is true?
Maybe for every bit I'll replace it with the binary of that bit or something.
So you just do the raw encoding of this. You take the bit, if you gamma, you encode it in binary, that at most takes log gamma, this one, and you have to adapt the transition rules to work with this. You increase the state space possibly larger by a factor of gamma, and you can do this. This is not hard. We will see this. If I time permits, I'll see this. Some of you can stare at this and check this is true. Similarly, another thing I want to claim you can do is, so what these are all the various robustness. That is, I want to say the number of tapes. Number of tapes also does not matter. As long as k is greater than or equal to 2. That is, you can simulate any k-tape machine on a 2-tape machine with just a constant overhead. And but you can, I want to say furthermore, what I will actually, the claim I'll state is, can simulate a k-tape Turing machine over a single tape Turing machine with at most a quadratic overhead. What do I mean by that? By the way, when I mean single tape, there's only the input tape now, which is a read-write tape. When I mean single tape, there's only input tape and it's a read-write tape. Previously, we worked with several tapes, the input tape being a read tape and this one. So a single tape over here, I would just mean, so for our course, we will actually work with, we will not work with single tape unless I specified there is only input tape, which is a read-write tape. Notice this is slightly different from, if most of you have read Sipser, Theory of Computation. Sipser, throughout his book, he uses only single tape Turing machines. We will not be using single tape Turing machines. And I will point to this why in the next lecture. We'll say why we don't use single tape Turing machines, because they don't seem to be realistic. That is, they don't seem to exactly capture. They have a quad, and the reason they are not realistic is this: they have this quadratics. They have this quadratic slowdown. And we'll talk about this next time. All I want to say is right now, the definition of Turing machine, which we talked about, seems like a very specific definition, but actually you can tweak the definition in several ways. One is with respect to alphabet, with respect to number of tapes, with respect to single-sided tape, or double-sided tape. Right now, we talked about only single-sided tape. Tapes that only in one direction go to infinity, other direction halt, but you can talk about tapes that are both direction. You change all of these the definition is robust. You don't really lose anything in any of these. This, and then what we'll do next time, we'll formalize some of these. We'll define the notion of a universal Turing machine, and then we'll get on to more like the time complexity classes. That would be the PNP and polytime reductions. Stop with this for now. Questions?
So the quadratic blow-up, can you just go up to the statement once again?
Yeah. I didn't formally write it, but yeah.
So is this talking about time blow-up?
Yeah, time blow. So what I formally mean is, you give me a k-tape Turing machine that computes a function f in time t. Then I can give you a single tape Turing machine that computes the same function in time t square.
So if we are only talking about time, I mean, I'm thinking even quadratic, like it's still like only like polynomial away from any other time.
It's a great theorem. It's a great theorem. It's a great theorem. It says that if you're willing to allow a quadratic slowdown, then you might as well work with single tape Turing machine always. You can just, this claim, what claim I state here states that if you are fine with quadratic slowdowns, single tape Turing machines is, you can work with single tape Turing machines. So if your course of easiness and hardness is only between polynomial and non-polynomial, whether you work with single, you can as well work with single tape. But we haven't yet defined what easy or hard means. Suppose I want to say easy is n log n or linear time. Then quadratic Turing, then single tape is not the right this way of doing it. For example, let's actually, now that you asked the question, let's take the simple problem, a palindrome. I give you an n-bit string, and I want to check whether it's a palindrome or not. How would you solve this on a 2-tape machine? How would you solve it on a 1-tape machine?
Yeah, 2-tape machine, you could probably have 2 counters. And
so 2-tape machine, you can just move, you copy the input, the whole input onto on the other work tape, and then just move. You just copy the whole input to another tape, and then you can just move right to left and see if everything is fine. So it's actually a linear operation. It's an order n, you can do it. But 1 tape, the most natural way of doing it, you check the first, you go all the way to this one, check if it's correct, come back, check. This is the most natural way. It takes quadratic time. And actually, you can provably show that it takes quadratic time, that you can't do anything better than quadratic for a palindrome. Therefore, this quadratic overhead, which I said, is actually necessary, and you won't take anything more than quadratic. So if your notion of easy, hard, or what you want to separate is you just care about polynomial, we could have worked with just single tape Turing machines. And in fact, this is what Sipser does in his book, because he doesn't go into finer grain complexity. So he's fine with working with single tape Turing machines the entire book. But if you want to care a little more about this, then it's best to work with 2 tapes onwards. And once you work with 2 tapes, you can more or less simulate everything. Most realistic computation, you can simulate it with at most a constant overhead. Any other questions?
Also, the number of tapes is like mostly constant, right? K.
No, that's a constant. These are all, those are initial parameters of our, so we are not allowing the tape. So these are all fixed constants, K, gamma, Q, delta. These are fixed. This is a constant size representative. That's constant. That doesn't grow with the input. So we are working with, this is a fixed, whatever I have here, this might be very large, but it is constant. Whereas the problems you're solving it on larger and larger inputs.
Yeah, okay.
Silly question then is not, isn't cloud computing somewhere where this changes the number of tapes?
So the way I would view the cloud computing, no, it depends for what you mean by cloud computing. Cloud computing is one way in which there's a server and a client sitting there. You're talking more about in which there are several people. It's more like distributed computing. There are multiple people talking.
Yes,
There I would think,
let's say.
there I would think of it as multiple people. That is, there are several Turing machines operating together on this one. I would talk of each individual client or server as a player, as itself a Turing machine, and then there is communication across these Turing machines. But each of them I would model it as one single Turing machine. In the Turing machine, the way I modeled it just now.
Okay, fine.
Yeah. Any other questions? Yeah, this was a bit dry because of Turing machines on this one. Hopefully, when we come to reductions and stuff next time, it'll become a little more. This one. The first few lectures will have, there'll be a lot of Turing machines. It'll be fairly dry material on Turing machines, but we'll soon come to talking about problems and connections between problems, which will make it hopefully will be more exciting than this. Yeah. Okay, then. Yeah, we'll meet on Wednesday.
Thank you, sir.